This is comparison theorem, and what we're going to be using it for is to use another function to show that one function is convergent or divergent. So we have two functions, f of x and g of x. F here is bigger than g. And so since we're finding the area from a to infinity, right, and our x is going off to infinity, then obviously the area under the curve for f would be bigger than the area under the curve for g. So using that, if our function f converges and it's bigger, so like let's just say that e equals 10, right? This is just an example. Then that would mean that g would have to be less than 10 because, well, f is bigger than it. So if this goes to 10, this has to be less than 10, meaning it's convergent. So it's basically putting a bound on it. If you can find a function that's bigger than the one we're trying to find the integral for, and it converges, then so does the one that is smaller than it. And the opposite way of thinking about it is if g is divergent, so this one goes, say, to infinity, and f is bigger than g, well, guess what? It has to also go to infinity because it's bigger. So if it's bigger, then it has to diverge. So if you want to show that something is convergent, all you have to do is find a function that is bigger than it, and if it converges, then the function itself has to. So you find a bigger, I like to say, bound. And if you're trying to find something is divergent, then you find a smaller divergent. So something that is always smaller. And these aren't as difficult as you think. So this first one, by the way, is a typo. It should be 1, and I don't want to go back and fix it, so just make it 1. So if we want to show that this is convergent, and we know it is because, look, our degree is 3. So we're going to use that rule. So if we say that x over x cubed plus 4, and we can find something bigger than it that diverges, so we want something bigger, then we can also say that this diverges. Well, if you think about plus 4, whenever you have fractions, like 1/4 and 1/2, the bigger the denominator, the smaller the fraction. So if this is bigger, then the whole thing is smaller. Smaller number. So bigger denominator, smaller number. So if we were to get rid of the 4, we are in a sense making it bigger because we're making the denominator smaller. So by removing this, we are making this smaller, thereby making the entire fraction bigger, right? Smaller denominator. Bigger fraction. Okay, now you can just simplify it and you get 1 over x squared. Well, that's something we like. So we know that this has to be less than, from 1 to infinity, of 1 over x squared dx, and we already know that converges because our p-value is greater than 1. That's from video C. So we know this converges. So because this converges, this has to converge. Let's look at this with the graph too. So this is the 1 over x squared. See how it lit up? And then that is our function we're trying to find the area under the curve for, right? So you can see it's going to converge. You can even look at the number, how it's getting closer and closer and closer to some decimal here. And so if this equals 1, which it does, the red one, then that would mean that the green that's below it has to be less than 1, which means it's converging. So if we find something bigger than it and it converges, then so does the one below it. So if you're looking for convergent, find something bigger. And then vice versa, if you're looking for something that diverges, well, we want something that is smaller. So if we can find something smaller that will diverge, then the function that's bigger also has to diverge. So if you remember with sine squared, that's the easiest one to go after here. Sine squared x has to be between 1 and 0. Has to be bigger than 0 or equal to it, and less than 1. So we know that this right here, the smallest it can possibly be is 0. So this has to be bigger than or equal to 1 plus 0 squared radical x, which is equal to 1 over radical x. So we can actually put an equal on there too. And we put that 1 over radical x here. And that's a p equal to 1/2, right? So p equal to 1/2 means this diverges. So if 1 over radical x diverges, well, then this one diverges as well. Let's look at the graph. It's always good to just plug that one in and that one into your calculator and look at them, and they will show you if they are actually bigger than each other or smaller. So you can see that the green function here is bigger than our function, and we just showed that the red function will diverge, right? That this is not going to converge, which means our green will also diverge because it's bigger. So if the smaller goes off to infinity, well, this one also has to go off to infinity. And you can see that's what's happening. You can see it just keeps getting bigger and bigger and bigger and bigger. It's going off to infinity slowly, but still doing it. So again, if the bigger converges, so does the smaller. So if we find a bigger function than the one we're looking for, and we can show it converges, then so will the smaller one. And if we find a smaller function that diverges than the one we have, then we also show that the bigger one diverges. Well, what if part of it is bigger or smaller? So let's look at this one. So our e to the negative x squared does not have a antiderivative. So finding the integral is going to be really, really difficult. But we do know e to the negative x. That's something that we can compare it to. So now all we have to do is look and see, well, is it bigger or smaller than this one? And then we can look to see if it converges or diverges. Well, there we go. The red is our e to the negative x, and the green is our e to the negative x squared. And we are going from 0 off to infinity. So we know this green part right here is fully continuous from there to 1, where they intersect. Right? So from 0 to 1, it's going to converge, the green one. Right? We don't have to even worry about that. Green is convergent from 0 to 1. And then after that, you can see now that e to the negative x is greater. So if we can show that e to the negative x converges, then we're also going to show that the e to the negative x squared converges, because the e to the negative x from 1 to infinity is bigger than the function that we're looking for. So what we're going to do is take this and split it up. 0 to 1, e to the negative x squared dx. We're going to move these over and out of the way. And we know that this converges. Plus, and now we go from 1 to infinity, e to the negative x squared dx. And so now all we have to do is show that that converges, and we know that the whole thing converges. So we have to show that this is greater. And we already did graphically. You can already see that from 1 to infinity, right? These are greater than or equal to each other. They actually equal each other at 1. So we can say that this right here, right, is less than or equal to the integral from 0 to 1, e to the negative x squared dx, plus the integral from 1 to infinity of e to the negative x dx. Now, if we can show that this converges, we're good. So all we have to do is our normal limits. The limit, as t approaches infinity, 1 to t, e to the negative x dx. And it's a nice quick integral. That's why we're using e to the negative x. And we picked negative because there was already a negative there. So the limit as t approaches infinity, and then the integral of e to the negative x is negative e to the negative x, t and 1. And we plug that in. So limit. And then we get negative e to the negative t minus e to the negative 1. And so this would be plus. And so this we know goes off to 0 because it's a negative t, so it's decaying. Even if it's negative or positive, it doesn't matter. So this is 0 plus 1 over e. But long story short, it converges, because we got a number. So this one converges. This one converges. Therefore, our function is going to converge. So that means we actually do have a value that this is going to get. We're not going to go off to infinity or negative infinity. It does converge to some value because our e to the negative x is bigger than this one. And so if this one's converging to some number, which is 1 over e, then we know that this one actually has to converge to something that is less than 1 over e. And there you go. So, again, if you're looking to see if something converges, just find something that's bigger that converges, and of course that one will converge. If you're looking to show it diverges, find something smaller that diverges and show that that diverges, so that one would have to diverge. If you need to cut it up, go ahead and cut it up. It's completely fine, because when you cut it up into those parts, just make sure that that part does converge, and then now you can just look at that one all by itself. Or vice versa to show that that diverges, and if that diverges, well, the whole thing diverges. So again, these are just comparisons.